Good afternoon, everyone. Thank you for attending my talk. The title of my talk is The Zen of High-Performance Messaging with NATS. Quick introduction about myself. My name is Waldemar Quevedo. You can find me on Twitter at WallyQS. GitHub is the same. I'm a software developer at Apcera, based in San Francisco, where I do the development of the Apcera Trusted Platform, which is an on-container orchestration solution. And for a further background, in the past I was doing development and operations from a platform service at a large e-commerce website in Japan, which was based on Cloud Foundry. And that was using NATS as part of its control plane. It became a fairly large deployment, so that's how I became more familiar with doing operations around NATS. And I'm also a maintainer of a couple of the client libraries for Ruby, Python 2, based on Tornado, and async.io for Python 3. So about this talk, things I want to share with you is first, what is NATS? Then what is the design behind NATS, how it works, and why I like it. Then move on to start talking on how can we start using NATS for building distributed systems. So let's get started. And what is NATS? NATS is a high-performance messaging system. It was created by Derek Collison, originally in 2010 for Cloud Foundry. It was first written in Ruby with Event Machine. Then there was a rewrite in Go in 2012, which gave it a lot of many performance benefits. It is open source under the MIT license, and you can find it at GitHub under the NATS-IO organization. It's a very small binary, thanks to Go, the Go team, and there's design decisions there. It is only 7 megabytes in size. It's one of the smallest, it's a very small Docker image as well. It's a single binary, so it has very few layers, and has no other deployment dependencies. So that's very convenient. In terms of the project, one of the goals of it is that it tries to act as an always available dial tone for different clients to be able to communicate with the service. And well, of course, one of its main characteristics is this the performance, which if you use the NATS bench micro-benchmark tool, which is available in the repo, here we're sending 100 million messages. You can see that you can get a throughput of around 10 million messages per second with a single byte, which is still a micro-benchmark, and which could be quite impressive. But for much thorough benchmarks, I highly recommend the blogs from Tyler Treat, which is in the audience. And there he makes a much better comparison of how NATS fares and what are some of the trade-offs involved, because there are trade-offs involved in NATS compared with these other messaging systems. So this is the link at the bottom. So we might need an update some of these because NATS has been evolving as well there. But this talk is not mainly about only performance, but how NATS keep things simple. So NATS has simplicity and performance as its main traits. So moving on to the design behind NATS, NATS has a design that was kept constrained so that it's operationally simple and reliable as possible, but without compromising both performance and scalability. This is because simplicity matters. And you're will be familiar with the work from Rich Hickey. There is a great talk on the RailsConf a couple of years ago where I was fortunate to attend and really like that. I recommend where he explains that simplicity buys you opportunity. And then he goes on to define that there is something called like architectural agility. And by architectural agility, he means that having a system that is the one you get by having a system that is fundamentally simple. And that type of agility dominates over any other type of agility. And how NATS achieves simplicity? It does so by having a concise, a strictly limited feature set. It does nothing but pure publish subscribe. So unlike other messaging systems, for example, it doesn't have built-in persistence of messages. It doesn't have any exactly once delivery promises. Instead, those concerns are simplified away from NATS. As a thought exercise to put in the minds of what what is the problem that NATS is trying to solve is think of yourself what could be the fastest, simplest, and most reliable way of writing and reading to a socket to communicate to one-to-one, one-to-n number of nodes. For NATS, this means choosing TCP/IP and having an always established TCP connection with the server. And over this always established connection to the server, you use a very simple plain text protocol and do nothing but pure publish subscribe. And it is a fire and forget system. In terms of delivery guarantees, you could say it's a must once delivered, meaning that if someone is not plugged into the system and interested into a subject, then that message will be just dropped into the floor. And this is the NATS protocol. It's fairly simple. It's very few number of commands. You can publish messages, subscribe into a topic, unsubscribe from it. From the server, you would be receiving messages. And there's a ping and pong, which both the client and the server send each other. And initial info, which tells the client how to handle the connection with the server. And also the client can send these connect payloads to label its connection. And there's a couple of error notifications as well. So I will just make a quick run through to the protocol. This is the demo public site, so you feel free to try it as well. This is a very simple client, and telnet demo.nats.io on the port 4222. The first thing we get is this info string, which is going to tell you whether the server requires, whether we have to start TLS, and also what is the maximum payload size that we can use for each one of the published messages to the server. And yeah, we can send an optional connect command. It is, you have to send it in case the server requires authentication credentials. But here we just label on connection as a NATS strange loop client. It has to be a JSON string. Of course, we can send a ping and receive a pong back to the server, which can be useful to measure the round trip latency. And if either the client or the server don't do this periodically, and by default this is an interval of every 2 minutes, the server will chop the connection off and take it out, take the client out. And this is the basic subscribe functionality. So here we express interest on the hello subject, and we use an arbitrary identifier with number 10. This is for the local logic from the client. And if we send 5 bytes on this subject here, you can see like there's a number 5, and in the control line, this will make the server expect the next 5 to read the next 5 bytes, and if he doesn't follow that, then we'll consider that it's not following the protocol and also disconnect the client. But if everything goes well, then we will receive this in uppercase message on the hello subject, which is matching with the original subscription we made, and is telling the client to read the next 5 bytes that the server is sending. So here we have sent our message to ourselves. Something important to highlight here is that the payload is opaque to the server. So for the server, it is just bytes, and meaning that it could be really anything. You can use a JSON, message pack, protocol buffers. That's up to the client libraries to decide. And so this is okay for doing one-to-n broadcast communication. So let's talk about like how does NATS achieve doing one-to-one communication with doing nothing but pure publish subscribe, right? So the problem here is how can we send a request and expect a single response back with nothing but pure publish subscribe? The way NATS addresses this is quite interesting, and it does so by having these ephemeral subscription inboxes, and they work the same as the other types of subscription, so it is still pure publish subscribe. And the NATS client libraries, they have helpers to be able to create these random strings, and all of the client libraries, they're quite sensitive to the reliability because there's randomness involved. They are sensitive to the reliability of the available pseudo-random number generation that you have in your runtime. But this is how you can use it. For example, in the Go API, this will give you a unique inbox you can use and then express to the server that you're interested in this subject, giving an ID. Then we tell the server that we have limited interest in this topic, and we only want to receive a single message on this subscription that we have locally identified with a number 2. Then we move on to actually publishing the message. And here we're sending a message on the health subject, tagging it with this ephemeral inbox, and telling the server to read the next 5 bytes that we have, so please. Then if and only if there's another subscriber connected at that moment and interested in helping into this subject, then it will be receiving a message matching to that subscription that it had done previously, and it will perceive the inbox that this other client has sent, and then we'll reuse this inbox to make a reply onto that subject directly. And finally, if the original requester is still connected to the server and it has not received any other messages because we're only interested in receiving one, because so the first one will win, the server will send the message to this client. So here's 11 bytes telling that I can help. And this is roughly the core functionality from NATS, and everything just builds on top of this. So I guess I hope you can get an idea that it's a fairly simple protocol, and because it's a simple protocol, you have also very simple clients. And all of the client libraries tend to have very small footprint. They don't are like this not thousands and thousands of lines of complicated logic. The NATS Go client is, well, I have to double check, but it's very small. And we have many of these. Original implementation was the Ruby-based client using the event machine. But now the canonical implementation is the Go client. So other client libraries reference the implementation from this one to see what are the features that they have to implement. But now there are many more available. So officially, the NATS team is supporting like C, C#, Java. There's a couple of Python ones, Node.js, and Elixir too. There are many contributed by the community too. There's even one for Nginx. This one is quite interesting, and is what we use at Apcera for dynamically getting notification of where to reverse or proxy the routes to the applications that are running inside of the cluster. So we don't do any kind of like reloading of Nginx configuration or yet another proxy that is going to be doing that. So it's just like by having an Nginx hooked into NATS, it will almost instantly know where to send the traffic. So yeah, I think that's pretty cool. Yeah. And something important to note about the clients is that they're asynchronous mostly. So they have asynchronous operation. They do asynchronous I/O. Here, this is an example from the Go client where you're interested in the hello subject, and we're sending 1,000 messages. But at this point in the code, there is no guarantee of having actually sent these bytes. So we have to do an extra step if we're interested in ensuring that we have actually sent this. Reason for this is that there is our internal engine built into the clients where they do coalescing of the writes in order to get not just be writing to the sockets all the time. So in order to ensure that we have actually sent all of these messages, we append an extra ping at the end of the buffer, and we make a future so that we're expecting a pong back from the server. And this way we can ensure that the server has consumed all of the bytes that we're sending and in the order that we write into the socket. Coincidentally, this is one of the worst ways of measuring NATS performance. Like sometimes, like there are new users from NATS, and they hear that it has good performance and it's really fast. So they make this simple loop where they're sending as many messages as possible, and they have this other subscription, and they try to measure how long did it start to finish consuming all of these messages. And it's quite funny what happens when you try to do this. So here we have in the top screen the client sending as many messages as possible. In the middle is the server. And you can see that there's this slow consumer detected errors being logged into the server. And at the bottom, there's a small utility that I wrote in Go. It's NATS stop, which monitors, gives you this terminal UI to monitor the server. And you can see there's a slow consumer count increasing. And so basically, the original client is becoming disconnected and then trying to reconnect and disconnected, trying to reconnect, trying to send all of those messages, but the server is just disconnecting it. Reason for this is that the client is becoming a slow consumer, since it said that it was interested into this hello subject, but because it is so busy at sending all of these messages, the server has to continuously increase the pending data size from the client. So at the point this could affect the whole service, so it becomes unsustainable for it and it will just disconnect it. And basically the NATS server is protecting itself. This is because NATS is not only performance and simplicity, it's also a resilient messaging server, which is kind of the three main traits that define the implementation of NATS. This is not all the features that it has. There's also subject routing support with wildcards. You can do authorization rules on them. There's distribution queue groups, clustering mode. As I said, you can upgrade to a TLS connection and has monitoring endpoints like bar-C style, from which you can get the state from the server. This is an example of how the wildcards work. Here we have a separated subject, where we can, if you use the asterisk wildcard, then it will match to anything that is published on this subject, matching to this wildcard. One example from this is, since we know that all of the NATS requests are going to be underscore uppercase inbox, we can subscribe to all of the requests that are happening through the server by using underscore inbox dot asterisk. And there's an even stronger wildcard, which is called the full wildcard. This one will match everything after the dot that is published on the server. So if we make a hello dot full wildcard subscription, this will match messages such as hello world dot again. So it continues to match. This is very strong. So if you try to connect right now to the demo.nats.io endpoint and subscribe just on the full wildcard, you will start seeing all of the messages that are happening right now in the server. So yeah, I think someone is publishing some JSON messages all the time. And if you try to publish on the underscore sys, you can see that the server disallows you because it is reserving that name for internal messages. And you can customize this by having a static configuration from the server where, for example, you can have a Bob user only being allowed to make requests and Alice user being able to subscribe and publish to anything. This is roughly some of the, well, most of the feature set from NATS. So next, I want to start covering on what are some of the examples from actually using NATS and building distributed systems with it. So this is a familiar scenario for many, I think. So we may have an external API server receiving requests by an external load balancer, and this one, by each time that is receiving a request, we'll have to talk with these other internal services, like some service E, which then has to talk to this other service B for internal communication. And if we horizontally scale this deployment, then it might look something like this, where everything is point-to-point connecting to each other, and it becomes the whole Death Star microservices kind of thing. And then we'll have to start thinking about how to do communication within this system. And we may think, should we just use HTTP everywhere, or some forum point-to-point RPC? And we'll have to solve the problems of how to do service discovery and load balancing of the services. And if at this point we are interested in concerning having a sub-millisecond latency performance, yeah, it can get interesting. But this is because it's the nature of distributed systems, right? Which is tend to be these levels of fun. So what does NATS gives us? NATS gives us basic publish-subscribe-based low latency mechanism for communicating one-to-one, one-to-n number of nodes. And we have this always established connection to the server. NATS is not a system where you have to create a new connection for each one of the requests that you want to send. It is meant to have always this connection and basically have a dial tone. So it is supposed to be easy to use because it lays near in the literal implement definition, easy. And so communicating through NATS may look something like this, where we have all of the services that are plugged into NATS. Then you may think, but then this makes NATS become a single point of failure, and I don't really want to have single point of failures in my distributed system. There's a way to prevent this by making a full mesh cluster mode from NATS. So this way, you can have your different services connected into one of the NATS nodes. And they don't necessarily have to be the same node. If you see the arrows here, we have these services connected to this node, and these are connected to this one. And then full mesh one-hop clustering mode from NATS will be routing the messages through all of the subscribers and publishers. And because of thanks to the built-in client reconnection logic, whenever one of these nodes goes away or dies or crashes, well, yeah, the client libraries will reconnect to another immediately available server. And the API for doing this is just use a comma-separated list of the servers that are available. But there is a bonus. Now the clients, as of recent releases, they can discover the topology from the cluster dynamically. This is an example of the auto-discovery. So let's say that you have your infrastructure in AWS or some cloud-based deployment, and you create a box where you're running NATS, and you don't really know what are the other IPs from the other cluster nodes, but you create one, and then tell them this new NATS server where the other server is. So this will create the mesh, and as soon as you do this, the original server will notify all of the clients where is the new member from the cluster. And all of these clients will reconfigure automatically and be aware of where this other NATS server is. And if you add yet another node, the same thing will happen. And now the clients are aware of the full cluster topology, meaning that if this server dies for some reason, well, yeah, here they're all connected now, it's all good. But if the one goes away, by default, they will randomly try to reconnect to one of the other immediately available nodes within the cluster. So I'm talking about some examples of how to actually use this NATS for communicating. Very basic example could be, for example, doing heartbeats. And this is a very basic mechanism, for example, to publish. You can have your services periodically publish heartbeats on a subject so that you can express the liveness of the service. And you can leverage these heartbeats to create some sort of discovery as well. So here you use the wildcard on the on the service dot asterisk dot heartbeats, and you will receive all of the other publishes from the nodes. And so you can discover is, who else is talking inside of the cluster. And also, NATS also supports distribution queues. And the way to use distribution queues is when you, well, the use cases where you don't necessarily want to broadcast all of your messages, and rather you want to distribute the work between a set of workers. And the way to do this, to use this functionality is by having making a subscription, and just like the other subscriptions, let's say service.a, separated by space and workers. This will create a distribution queue named workers. So now, if we publish a message on this service.a, each one of these messages will be balanced randomly among the these different service nodes. So it's not broadcasted anymore. Each one of them will receive it randomly. Yeah, it's not round robin, randomly. And the API for doing this is queue subscribe. And here we are subscribing to the service A and using the name workers for this group. Something important to note of NATS, the way the distribution queues work is that NATS does not assume the audience, meaning that you can have multiple distribution queues from the same subject. So here we have, we're subscribing to service A using distribution queue named workers. We could have in parallel also a service.a helpers distribution group, and even a wildcard which will be matching on anything that is service.a, b, c. If we publish a message, they all will be receiving the message, right? So NATS is, does not, well, this is what we call by not assuming the audience. And this is where NATS really shines. And if we were interested in having the lowest latency response from one of the service nodes, by the very definition, by the very definition of the NATS request, the first message that you get back from a request in NATS is the one with the lowest latency. And so this is where NATS, this is because the NATS requests were designed for this, basically. The API for this is the NATS use the connection and send a request on service V. For example, telling with the payload, and in the API from the clients, you need to give a timeout, a client timeout, after which you will give up waiting for this message. But if there is other subscriber on this service being willing to help, then this other subscriber can use this inbox to reply back and request help back. And something important to note here is that since the messaging system, and you need to be more careful with the error handling. So for example, the reason why something failed could be many things. So from the client side, you're only making a request and expecting a single response, and let's say that you hit the timeout. This could have occurred for a number of reasons. It could have been the case that the service was unavailable at that time, and there was no one really connected into the system. Or maybe it did receive the request, but just the service took too long to reply back. Or maybe it was processing the request, but it crashed while handling this. So we need to be more careful how to do error handling in these cases. And for example, if we want to confirm that service is available, we could have all of the services have its own inbox, and then might make an extra request to get basically to check if there is anybody out there willing to help. And then this other service could reply back with its own inbox, and then we use that that inbox to make an extra request and communicate directly to this service node. And so, yeah, okay, so just to summarize, and NATS is a simple, fast, and reliable solution for the internal communication of a distributed system, and especially if you're flexible when how to handle the internal communication in it. And it does choose simplicity and reliability over guaranteed delivery, but this does not mean that NATS will constrain the guarantees from your service, right? If you were at the Papers We Love conf that happened a couple of days ago, there was this great talk on the end-to-end, which covered the end-to-end argument, and there it was saying that this type of guarantees for your application, you need stop relying on lower subsystems and instead like code them up in a higher layer. Because and you can, if you don't do so, by having this older optimization in lower layers, you can end up wasting your time and causing confusion, since there's no guarantee that it will give these guarantees on the higher layer. And there's even a stronger variation of that argument, which even causes, it is harmful to do so. So just to quoting Tyler Treat, who gave a great talk about NATS, and he put it very succinctly, I thought. We can always build stronger guarantees on top, but we can always remove them from below. And meaning that if we start thinking in terms of, for example, designing our system to be able to replay the messages instead, and then that becomes more important than having just guaranteed delivery. And if we can design our system so that you can safely retry the request, that can be better than having exactly once delivery. And also, if our system is, can sustain having rearranging of the messages, this can be better than just having other delivery. And our system could end up being more resilient by following these traits. But again, this is not NATS. There's a related NATS project which is trying to address these concerns. It's named NATS Streaming, if you want to check it out. So I'm okay on time, but so I was, that's it for my talk. So I really thank you for attending, and yeah, feel free to play with the demo site. And I think there's time for Q&A too. Yeah. Or I can demo NATS too.
When you describe the cluster of servers, it wasn't completely clear on whether is every message that's published then relayed out to all of the servers in the cluster, or is there something else going on?
So yeah, you have to, there's a routing happening between the servers. So if the server is aware of there's a subscriber interested in the subject, then it will be routing the message to this other node. Yeah. So this is NATS basically. Let's say. So yeah, this is a very simple example of using it. Yeah. Any other questions? Yes.
So in practice, like how often does it lose messages, even though there are no guarantees?
How often?
Yeah.
So yeah, that really depends on the on the application. So how often does the server loses messages? That's really not responsibility from NATS, from the way it was designed, right? So NATS will try to send the message, but if there is no one really connected to consume that message or receive it, then that was it for that message. I mean, it just got not be sent, yeah, not be received by anyone. Yeah. Yeah.
So you have to have a listener to receive the message, or there's no persistence. I'm assuming there's no persistence in memory for any amount of time.
No. Yes. So yeah, I mean, NATS is used on quite a few number of production systems. I mean, you can see the website to look at the full list of who's putting in production. I think like many of the deployments from Cloud Foundry, for example, they use NATS and they have deployment level applications as well. So yeah, I mean, it has some quite usage for the type of problems that NATS is solving. Yeah. So. Yeah, I mean, that sounds like a same use case, like for internal communication about components using as a control plane. Yeah, NATS is very suited for that. Yes?
This is really a question, actually, but could you bring back up your second to last slide and go by average?
Yeah.
There's some really good points on there.
Okay. Yeah. So NATS streaming is basically it mounts on top of NATS, and so it reuses NATS itself. It's not a NATS application, you could say. And on top of NATS, it creates this other layer where it tries to give you this type of guarantees, where exactly once delivery and replaying the previous messages that had been sent and no one consumed it, for example. So yeah, it tries to address some of the concerns that are in this slide, but I guess the point here is that those concerns were separated into different projects. And is that okay? Yeah. Mm-hmm. Yes. Any other question? Yeah. Yes.
Did you measure like the latency end to end from like sending a message to getting it out of the side, sort of the tail percentile of that?
So for that, yeah, luckily we have Tyler Treat in the audience, and he did a great job at showing that. So what is it? 10%. But I mean, we can talk later on this one. Yeah. Yeah. Okay. If not, then close. Yeah. If there are any more questions, then I would like to thank again for your time, and hope you like enjoy NATS and play with the demo server. And I'm around to talk if you want to check out the demo or yeah, I can help you. Okay, thank you.